Yeah, so I have basically says that, okay, under null hypothesis, you will have transition density available to you, like CIR, CEV, or even affine diffusion models. In theory, with smart financial mathematician working on it, at the end of the day, you get a parametric form. Now, you don't know if parametric form is fit adequately the data, so I compare it with non-parametric, that is, without any model form, I should also get the density by using just let's say bivariate density estimation. So this bivariate condition, and then you compare the difference. No, I know you know. I just want to refresh people before other people forget. So using this opportunity to give me another chance of review. So then I compute a few distances. Okay, so one distance is T1, which is the chi-square distance. T0 I could compute. I have trouble proving it, so I do T1. And you could do T2, which basically say, let me integrate those functions first and then compute that distance, right? This is T3, that I'm doing here. So this transition distribution based, the distance between transition distributions. And you could also do Hong and Lee's uniform transform to the uniform sequence. Now you could compute bivariate density distance away from uniform, and or you could test the cumulative distribution function using Karameev-Missos tests, or you could do bivariate version of Karameev-Missos test. So these are basically 6 test statistics I'm talking here, and the most difficult one, of course, is transition distribution based tests. So similarly, we could do transition distribution-based tests. So transition distribution-based test, I only localize in X domain because there's no localization in Y domain. Conditional on X, so I have to do this. So then the whole constant, everything looks very similar to Karameev-Missos type of theorem. And we basically say suitably normalize of your test statistics, which is by this number. And then it will be a asymptotic chi-square distribution with degree of freedom Bn here. Bn is of order 1 over H1. And again, we says that this distribution will have. This distribution independent of nuisance parameters under null hypothesis, and this allows us to do simulation, justify our bootstrap method, and this usually have faster rate of convergence because now I'm doing smaller degree of freedoms. Just like I have n data points, now I divide it only in x-axis into many sub-bins, so you get a transition distribution based on that. And what is the power of the test? Well, you could play around with mathematics. Valadier certainly played many years of this kind of mathematics, and I try to tell many people, nobody ever listened to me, including Joe Horowitz. I'm sorry, I didn't want to name anybody. They always studied this kind of null hypothesis. Okay, so the null hypothesis is, under null hypothesis is this is clear. Now alternative, you say, let me have some kind of deviation from the alternative. So note carefully here, I have put a function g here. So this is the speed of convergence go to 0. So this is really talking about global deviation because you shift the whole null density over by another function. And of course, this facilitates mathematical calculation. And then you could say, okay, under the alternative hypothesis, the null distribution goes to a asymptotic normal with whatever the biases coming up due to the distance or deviations, which is explicitly defined by here. I don't really want anybody to read carefully because then you'll find typos or mistakes, but just basically say something calculable, okay? And then people will get into the conclusion that you could get the rate of convergence of 2/5, okay? So this, no, I haven't said the differences. I need to have next slide to tell the differences, okay? So then you could show that, okay, this rate actually is optimal. That's Valadier played many years of this kind of trick. That is, if the distance d here, the constant d here go to 0, then you have no power less than alpha. D go to infinity, you have power 1. So this basically said the whole test is of rate of 2/5. So this is for this very, very specific alternative. I would say global shift, okay? And the local shift, then you could also talk about transition distribution, just integrate the whole function, then you have also global this. We could also compute the power explicitly, something similar like this, but I didn't present here just to make, oh, I did present here. Something similar like that, and with explicit formula all like this. And then you could show that rate of convergence in similar way is 4/9. And then certainly I got criticized, then why you use a transition density-based tests? Right, I mean, transition density-based test has rate 2/5, and that is 4/10, and this I have 9/10, so certainly a little bit better, right? So you may be asking why I do that, and my argument is that this kind of deviation is a global deviation, is more favored to transition distribution-based. So if I just do local deviation like this, which has also rate of convergence like delta m, but it's not global shift, just in a very small local neighborhood. Then in this case, transition distribution-based estimation, once you integrate with respect to y, you killed everything out, right? So you will not see any distribution different. In other words, two distribution could be very close, but its density could be far apart. So global type of tests have little power in detecting this kind of alternative. And this kind of alternative is much harder to prove mathematically. So for this reason, most people lazy using this, but doesn't mean it's always a correct formulation. Including myself, I'm doing here just for mathematical convenience. Any questions? Yeah? Mm-hmm.
So in your procedure, you first mentioned the number of proposals for the choice of the benefits, and so in your array computations, actually you selected the array of benefits.
Mm-hmm.
Plug it in. If you think about the data-driven version of this, so another alternative in testing is what actually you developed.
Mm-hmm.
Well, is to apply a multiple testing.
Mm-hmm.
This means you try with different methods and apply the multiple. Then you apply the statistics somewhere.
And I agree with you. Actually, as early as 12 years ago, when you were young and I was young, if I didn't forget anything, that I wrote a paper in JASA talking about multi-frequency adaptive enablement. You wrote a paper in Annals of Statistics using the multi-scale wavelets. So certainly I understand. And so in 2001 paper that I wrote on generalized likelihood ratio test, I say multi-scale didn't prove anything. I'm aware that Joe Horowitz and you did in econometrica paper do that multi-scale. Now you could do that. You can play all the games. I'm just saying that, that will give you an automatic choice of bandwidth depending on the complexity of alternative hypothesis. That is the degree of smoothness under the alternative hypothesis. So we could have done it here. But I'm trying to say is if I put in this kind of null hypothesis, global deviation, then I have little choices here. I mean, the transition distribution base is always perform better, no matter how you choose H2. Unless you choose H2 equal to 0, then it will be the same. Otherwise, it's always better because it's just simple because I have no local deviation here. So now if I thinking of local departure, that is there's a very small interval that shifted by a via delta n, then I think density-based would be better. I'm trying to defend density-based estimation has its value, even though mathematical doesn't show up because our formulation is not wide enough to consider that case.
Actually, this is the second question I would like to ask. This 2/5 and 4/9. So actually, in the hypothesis testing theory, in the integer, there is a general rate of testing, which is 4 beta over 4 beta plus 1. Or 2 beta over 4 beta plus 1. And so this formula is actually for two different betas, beta equal to 1 and beta And could you interpret that in this example we have just double smoothness?
Right, right. No, no, yeah. No, I agree with you. No, I really agree with you. I'm trying to tell people, not look when you're looking at this kind of alternative hypothesis. I mean, the first kind, global deviations. You always see that. I mean, the global deviation is better. I mean, but there's many functions not included in this class. So that's what I say. I think I have no different from what you are saying. Maybe, yeah. Maybe a little bit different in terminology, but it's really similar to what you said. I mean, we could have done that, but unfortunately, my mathematics is not just as powerful as you are. Otherwise, I should be able to crash all of those over. But certainly, I'll get rejected too. I mean, the paper will get rejected too. That will be another problem. Pardon? Oh, okay. Oh, I'm glad if somebody say disagree with my statement. I'm happy. Forthcoming, okay, forthcoming, okay. Okay, so now let's see, I mean, let's just do some simulation to give us a rough idea what it looks like. Okay, so I have more simulation than what I presented here. As I say, I have jump diffusions, which really fall in the same category, but unfortunately I didn't present here. So I generate 2,400 weekly data and 1,000 simulation. And to make everything null hypothesis trackable, I just take in lazy Vasicek model or OU process with kappa, mu, and sigma getting from fitting treasure bill data. So this is like close to real data, as close as I can. Alternative, my testing is Vasicek model against stationary time series. No more than that. Okay. So now, of course, the power depending on what kind of alternative you are detecting. So I'll compare. So in other words, if we go back to this picture, I'm really doing this, right? So, okay, now hypothesis Vasicek, alternative is here. Yeah.
So what's the econometrics name for discrete Vasicek model?
Econometry name? OU, you mean? OU is mathematical name. Uhlenbeck.
For certain parameter values, it's equal to a regressive process? Or
Pardon?
is it equal to an autoregressive process? Or?
Oh yeah, it is equivalent to AR1 model. Yeah, it is. Yeah.
That's what I'm saying. The econometrics name is R1.
AR1.
AR1.
Yeah, but you're talking discrete AR1 model equivalent to this. Yeah.
But everything is discrete in your world.
Fine. I'm not getting angry. I mean, I didn't. I'm smiling. Fine. I mean, if you want to call, let me generate from AR1, fine. But now how can I do alternative? I will have trouble of alternative. Now hypothesis, I have no problem. Now alternative, I will have trouble. So that's why I want to call the Vasicek model. I see, okay. Wolfgang is testing if I know this is equivalent to AR1 model. I know that's all your purpose. I know that. Hey, come on. Wolfgang, at my age, should be seeing many things. Come on. Okay. So now I need to evaluate at 3 family alternatives. Actually, we evaluate at 4 families. Actually, one of those is jump diffusion. But anyway, so the first family I do is drift doesn't change. Alternate, I mean, this part, volatility change a little bit. Instead of using a constant here, so I just index this by theta. Okay, theta equal to 0, then I really get the same null hypothesis, right? And alternative hypothesis, null hypothesis. So alternative, I just replace by a weighted, I mean, a linear combination of 2 model fit to treasure bill data. The other model fit is a CEV model, CKLS model, with gamma being estimated at 0.73, right? And sigma hat and so on. So this is really a linear combination of this. So if you like to see when theta equal to 0, my volatility function looks like the same as null hypothesis. When theta equal to 1, 0.2, 0.4, 0.6, math doesn't work, 0.2, 0.4, 0.6, 0.8, no. Okay, and then the last one is 1. Okay, so this is how we plot here. So, okay, but of course you see that they are quite distant, but most of the data is around the mean reversion, right? So most of the data is here. So really the difference is in this region, because most of the data outside here, even you rarely visit. I mean, the 2 processes never visit there, okay? And this is the invariant density or the local time, how frequent the interest rate. I mean, 30 has more often around 7% than around 4%. Right? So all I'm plotting here is 3 density corresponding to theta equal to 0. That is Wasilewski model, or that would be normal distribution. Now, in order to prove to you that I know what it is, looks very normal, remind me. And the theta equal to 0.5, theta equal to 1. So this is just a transition distribution departure. And here is the power, okay, of a few tests I summarize here. So this is transition distribution density based chi-square distance between 2 transition densities under null hypothesis and under alternative hypothesis. Dashed line here is based on transition distribution, look quite good. The red one here is Hong and Lee's methods. Compare the Rosenblatt transform and see if Rosenblatt transform now looks like a uniform distribution or not. And the other one is the Kolmogov's, Kramil-Mises test for univariate distribution, uniform distribution, or bivariate uniform distribution. So the power is clearly as theta changes. They have the same starting point, but the ending very differently. So it's clearly in this alternative hypothesis that our method is far more powerful. Okay, so the second family, I change, again, keep the mean the same, but just change volatility a little bit so that the difference is around this one on both sides. Okay, so symmetrical on both sides. So theta equal to 0, theta equal to 0.2, 0.6, 0.8, 1. I think this time I counted right. Okay, so so this is just theta equal to 1. So equal to 1/2. I think I should go back to Wasilewski model. Okay, so this is the difference implied, the invariant density implied by the different parameterization, just to give you roughly idea what the distance among those 3 densities in the real term. And in this case, I just want to prove that Hong and Lee's method sometimes can also be good. So just to be fair, and most people want to squeeze other people out of business. I try work hard to make somebody work one time. So this time is the best. Our two method is the worst. The transition and 20 worst, but not differ by that much. In this case, all methods are powerful, by the way. Kramil-Mises tests are also quite good. So this is just another example to show that. And now I could do another one. How about if I have deviations in nonlinear mean reversion? There's a lot of paper like by Chapman and Pearson and in Financial Journal of Finance. They are, discuss whether the mean reversion, nonlinear mean reversion is real or not real, and so on. Okay, so we are now doing nonlinear mean reversion. So reversion function could look like that at theta equal to 1, or looks like this at theta equal to 0.2, 0.4, 0.8. Oh well, my math doesn't quite work here, but anyway. So this is the nonlinear mean reversion. And volatility I keep the same as null hypothesis, Wasilewski model. So this is just the implied transition density, the invariant density differences among the family for theta equal to 0, 0.5, and 1. Okay, so just give you rough idea what is the distance implied by the univariate distribution. So now this time is always the case, people do this, right? So now this kind, our 2 method is far more powerful. And interestingly, Rosenblatt transform method has 0 power. Any of those method has no power at all. So this is, so Hong and Lee's method doesn't work at all in this case, and its variance doesn't work at all in this case. Okay, so this is, pardon? I think just because the transform, if you have more local deviations, the transform by Rosenblatt transform was just like integration of that, it will smooth everything out.
Yeah, because also in this alternative, you just change the mean.
Yeah.
You change the volatility.
Yeah, I keep rotate the same. Just.
And the question is then the relation of sigma to theta.
Mm-hmm.
And if you change this relation, then I think you also have power in Hong and Lee. Because the signal to noise ratio
changes, but it's the same horse run, right? All methods apply the same data set, so it's fair in some sense. Even though I know I change signal to noise ratio, but every method, if signal to noise ratio higher, everybody is higher, lower, everybody is lower.
to infinity, you want to say if sigma goes to infinity, you want to tell me that the Hong and Lee does never pick up power?
If sigma go to infinity, nobody.
To zero.
0, everybody will get some power, yeah. Yeah. Yeah, that's what I mean, yeah. Yeah, okay. Okay, good, yeah. No, I'm just saying that, so this is another example. You always say another example, just trying to see what the impact on nonlinear mean reversion. And then we could apply these to, to the real data, right? So VIX, data is a, I really don't know much about volatility trading, but you could, this is the, oh, it's close to 2:30. Oh, yeah, okay, so I have to be quick. Okay, so this is implied volatility, SP500 index at money, right, with time to maturity is 22 trading days, 1 month. So this is the implied volatility of SP500. And we got the weekly data from 1990 to December 2004. And we also apply to treasury bill data. And our null hypothesis is whether it's a CEV model or it's not a CEV model. So this is just 2 time series I apply here. Then you could estimate your transition density and transition distribution. So let me not go into any detail of this. But the conclusion is basically says that most of tests have no power to reject that the VIX data, that the implied volatility of SP500 in maturity in 1 month for a money option is more or less follow the CEVX, except this T4, Hong and Lee's method, why I do not give such a small p-value. And this is a transition density that we apply to treasury bill data, and all p-value are very small, except this procedure. So I think we have pretty strong evidence against the null hypothesis. And this kind of theory actually also apply to tests even more, ambitious, that is still work in progress. Yasin and I was still working on specification test for Markov hypothesis. So if Markovian hypothesis holds, then the transition density should satisfy this following equation, right? So if I transit from X to Y in delta time and transition from Y to Z in another delta time, then this gives me a formula called R to Z. So this is R to Z like this. And on the other hand, you could estimate directly transition density of this. On the other, you could estimate the directly transition density just using 2-step data. And now you are asking Chebyshev-Kolmogorov equation hold or not for this L2. So therefore, you could construct the distance based on convolution of these two 1-step density and the direct estimate 2-step density, or you could try the distribution function and the distribution function, and so on. So you could construct test statistics. We could derive similar kind of mathematical results. For transition distribution based, for transition density based, and power, and so on. You could just keep doing mathematics the same way. So we have done that. So since we have no time, I don't want to go there, but just basically, this is the idea of our tests. So I have, if test is, if process is Markovian, then Chapman and Kolmogorov equation have to satisfy. So now you could just asking whether empirical data satisfy Chapman and Kolmogorov equation, and so we did that, and we derived similar theory, and so on. So we are still doing numerical, calculation. So let me conclude. Is it okay? Oh, too fast. I thought we have no time. I didn't mean for you to see. I just showed the prove that I did do something. That's all I want to show you. I did do something. I did prepare. That's all. Okay, so yeah. So let me just quickly conclude. So generalized likelihood ratio based tests on transition density and distributions provide natural metrics for specification tests, because this is how you have null hypothesis implied transition density. You have alternative hypothesis implied transition density. So you would do Kuiper-Leibler distance or Hellinger distance. So they are optimal for detecting local, and this would be for transition density, and the global for estimation transition distribution. And we prove that the asymptotic null distribution independent of nuisance parameters under the null hypothesis. So therefore, Wilks phenomenon allow us to use bootstrap. And we, showed that, the test, is quite powerful for our for our test. And I mean, our model test actually is useful for like testing parametric models against a large family of alternatives. The alternative could include multi-factor models because we never even specify what alternative looks like, and so on. So I mean, as I say, Outlook will apply our procedure, which we have only derived theory. We haven't done anything yet. On the application part, whether the Markovian the process is Markovian or whether observed sample path is continuous. Are there any jumps there? I mean, there's, and so on. So we basically say there's a strong evidence against, weak evidence against CEV model for VIX data, but we have strong evidence against CEV model for TBO data, and thank you very much for your attention. Yeah, I think that's okay. Yeah, I completely agree with your idea, and actually you could do that. But of course, people also want to see horse run among different methods, right? So I showed the horse run without combining them together to be unified, United Nations. Like basically, you asked me to create a United Nations, which I could have done that. Of course, I mean, theoretically, there's free lunch by combining them together. I think what you have in mind probably is maximum, right? Rather than average. I think the maximum of the tests. But practically, there will be small power deterioration. I mean, small in finite sample, not asymptotic. Asymptotic doesn't matter. Power deterioration once you compare them, because in other words, let's say for this family alternative, T3 wins. So when you combine together, it will be a little bit lower than T3, but will never be too bad. So you are creating a more omnibus tests, which is a correct idea you could do to the empirical data applications. I agree with you. Horse racing is over, right?
Let's try to really make it 1 or 2 minutes.
Thank you very much. Thanks. Thank you. Thank you. Hey, thank you. So, thank you very much. You guys really tough. I know there's a lot of technical and highly incorrelated papers. And I know it's a lot of work for all of you, but I hope some of those will inspire some of your work, and that your work will inspire me back. And the questions and comments are always welcome. I mean, each time whenever I prepare my own talk, I feel that I have something else to do after I talk. It's always like that. People ask me questions, inspire me to think more. And the same way, so if you have any paper related to that, send it to me. I will very welcome that. Thank you. Oh, sure.